Alright, video I was surprised to find I didn't actually already have in my video libraries from years of teaching Chemistry 1 was a video on nuclear symbol, and I think a big part of that was because prior to the pandemic I kind of just did this in the course, and honestly I didn't think it took that much time to teach it in the course. So, chemical symbols. There are three numbers that we associate with any chemical symbol. So let's just draw, oops, pen started to die. Let's do carbon and oxygen. So when you look at the periodic table, this is what you see. You see these numbers here, the letters here. These are shorthands. So C is shorthand for carbon, O is shorthand for oxygen, something like Na is short for sodium. But there's other information we can put in there, and traditionally we leave this information off unless we really need it. So if we're writing carbon and oxygen formulas, we don't put these numbers in there because we don't need them. They're extra information. But if you were to write the full symbol, bottom left, what you're going to see is a number that refers to the atomic number. So this corresponds to the number of protons in the individual and the atoms. Now, the number of protons and the element are synonymous. So carbon has 6 protons, oxygen has 8 protons. And so one rule for chemical symbols here is that this and this need to match. You can't have C7, C12, anything like that, because that is a different element. So that's traditionally why this gets left off, and you're going to start seeing this pop up when you start balancing nuclear reactions, because the number of protons, electrons, and neutrons had to be conserved for nuclear reactions. Now, number we're going to see at the top right here is the oxidation state, and basically a few comments on this. First of all, this oxidation state is going to either have to be given to you, or you're going to have to be able to derive it, and I've got other videos for determining oxidation states of molecules, so I'd recommend you go to those. So this +0, +1 here, I've written here, they're arbitrary. They depend on the context, but it isn't true for all of the carbon or oxygen atoms. This number has to be calculated. But a comment about it. This is going to represent the difference between the number of protons and the number of electrons, not the other way around. So if we have a positive number here, we have a deficiency of electrons. We have lost electrons, that is oxidation. So carbon, neutral carbon, 0 here, has just as many protons as it does electrons, so it has 6 electrons. But if I write carbon +2, it hasn't gained electrons. The +2 here doesn't refer to the number of electrons gained, it refers to the amount, the charge. So if it has an extra +2 charge and you've got 6 protons, that means you've only got 4 electrons, so you've lost 2. If I do oxygen -2, I haven't lost 2 electrons, I've gained 2. That's how I get that -2 charge. So again, this is going to depend on the context more than anything else. But your top right here is going to be the oxidation state. And again, generally we don't write it unless there is reason to be writing it. But the other number is going to be on the top left. And you'll see these numbers written as integers because they are. And what this number represents is the sum of the protons plus the sum of the neutrons. It is not the number of neutrons. And this is the isotopic weight. So we write the isotopic weight assuming that it is just literally the sum of protons and neutrons. This statement is actually not true. It's a bit more complicated with the actual weight works, but if you're looking for a quick pass approximation, this is protons plus neutrons. So to figure out the number of neutrons, we just take this number and subtract off the number of protons. And we're going to say that this isotope weighs 12. Now, what really confuses students the first time they start taking chemistry is that if you look on the periodic table, carbon weighs 12.01. That is not a integer. You can't have a fractional number of neutrons. And so this 12.01 here represents the average atomic weight. So there are definitely isotopes of carbon. Carbon 13 is the most common isotope, but there are definitely other isotopes out there like carbon 14. So carbon 13 weighs 13, carbon 12 weighs 12. Neither of them weighs 12.01 because this is a weighted average based on isotopic abundance of all the different isotopes. So how do you know when this number is incorrect? Well, the thing is, students, there are two approaches I've seen students do, so let's just prove them one at a time. One, this number has to equal this number. That's not true. This is a weighted average. It makes no assumptions about which isotope you have. This refers to a specific isotope. So the fact that this number and this number don't agree will always be true because there's not a single element on the periodic table that has an integer weight. It's a weighted average across all the different isotopes. The second is to say that, well, this isn't a common isotope. That doesn't matter. And the reason it doesn't matter is isotopes can be created. They may be short-lived. In fact, most isotopes are unstable, particularly when you start getting above, I think it's atomic number 92, they're all guaranteed to be unstable. So the fact that it's not a common isotope or not a stable isotope is kind of a meaningless statement. There are definitely transient isotopes. If you look at the decay of uranium, there are isotopes that get formed that have lifespans on the order of microseconds, if not femtoseconds. They're still isotopes, they still exist, they're real. So the fact that this may or may not be a common isotope is no meaning. In fact, oxygen-18 is a highly rare, highly unstable isotope that's used in isotopic labeling studies and a lot of research. You're not going to see a lot of oxygen-18 out there, but the fact that it weighs 18 and not 15.99 doesn't mean you can discount that. So the only thing we can really say about that number being wrong is when the number of protons plus the number of neutrons doesn't make sense. So let's say I put 5 up here. Well, that 5 has to be the protons plus the neutrons, and I've got 6 protons from down here, so I must have -1 neutrons. We don't have antineutrons inside these atoms. So the only rule here is that the number up here has to be as big or bigger than the number of protons, because that ensures us that we have a 0 or higher number of neutrons. But if our weight, the top left number, is less than the number of protons, this doesn't make any physical sense, because we'd have to have a negative number of neutrons to get to that type of weight. So this is it for basically the gist of nuclear symbols. The only 2 ways to really show that the nuclear symbol is incorrect is that this doesn't agree with the element, or this gives you a nonsense number of neutrons.